Hello and welcome to this presentation of NOREBA. I am Ali, a PhD student from National University of Singapore. This is a joint work with Andreas Diavassos from UPC Barcelona and Terver Carlson from National University of Singapore. Current general-purpose processors hold onto critical resources like register file and load store queues longer than necessary. In NOREBA, we propose a better resource management for out-order processors based on true branch dependencies of the program. NOREBA shows higher performance and low overheads in terms of power and area compared to other out-order processors. By the end of Moore's law, we need more efficient processing. And these days, we use specialized hardware and domain-specific architectures to gain performance and efficiency. However, general-purpose processors still play a significant role in overall performance of the system, since the portions of the code that are hard to predict and hard to parallelize are left for the CPU. We need to rethink the traditional system design methodologies to unlock efficiency. Co-designing different layers of the system is a way to achieve this goal. Now let's look at the traditional design in current out-of-order processors. These processors execute instructions out of order, but they use a structure called reorder buffer, or ROB, to keep the order of instructions, which is a simple way to provide precise exception handling. Here, we assume to have a program with 12 instructions running on a core, that the execution time of each instruction is 1 cycle, and long latency loads take 10 cycles to get the data from memory. The size of ROB is 8 entries. In this program, you are going to have a long latency load that the branch outcome is dependent on the data of this load. Let's look at the execution and commit flow of this program in this out-of-order processor. Instructions are fetched and inserted to the ROB in program order. The processor always looks at the head of the ROB, and if the instruction at the head has finished execution without any exceptions, then commits and releases the resources of this instruction. You can see when the long latency load reaches the head of the ROB, it will block the commit of all the other instructions. Full ROB and not releasing the critical resources will block the front end from fetching new instruction, and as a result, hurting the performance. When the load is resolved, then the other instructions can commit one by one and release their resources. This is the in-order commit in current out-of-order processors. However, in-order commit is conservative and leaves a significant room for performance. What if we know that instructions 9, 10, 11, and 12 are independent from the branch in this example? Here is an alternative approach to commit the instructions from the ROB. If we know that an instruction is independent from the branch that is waiting for the long latency load, then it can commit and release its resources once its execution is finished and doesn't have to wait for the load and its dependent branch. You can see that we are able to save 4 cycles in this simple example. This approach is called out-of-order commit. In-order commit is efficient to implement and provides precise exception handling. If we want to gain the performance potentials of out-order commit, we have to answer 3 questions. First, how to detect branch dependencies non-speculatively. We need this information to be non-speculative in order to guarantee the safe out-order commit of instructions. The second question is how to implement out-order commit efficiently. Efficient implementation of out-of-order commit in the hardware has been traditionally challenging. Previous works tried to use expensive structures like a collapsing ROB to implement out-of-order commit. And the third question is how to handle exceptions when we commit instructions out of order. When an exception occurs and the control is given to the OS, we want to make sure that we know what changes the out-of-order committed instructions have made in order to recover properly from the exception. NOREBA proposes a hardware-software co-design to implement an efficient out-of-order commit processor. We use a static compiler analysis to detect the branch dependencies information and send this information to the hardware. And the hardware exploits the compiler information to safely out-of-order commit instructions that are independent from unresolved branches. As I explain more in this presentation, we use different commit queues for instructions that are independent from each other. Also, we communicate the out-of-order commit state of the processor with the operating system in order to be able to recover from exceptions. Here we are going to look at the compiler that we use in NOREBA. In our compiler pass, we go through 4 steps for each branch. First, we find the reconvergence point of the branch. Branch reconvergence point is the point in the program that the controller will reach that point regardless of the branch outcome. In this simple if-then-else statement, label L2 is the reconvergence point of the branch in basic block 1. Second, we detect control-dependent instructions, and these are the instructions that their execution is dependent on the branch outcome. In this example, all the instructions in basic block 2 and basic block 3 are considered to be control-dependent. Third, we detect data-dependent instructions, and these are the instructions that their data will be different if we execute different paths after the branch. For example, basic block 2 and basic block 3 both update 2 same locations with a store word instruction. So the instructions in basic block 4 that use these locations are considered to be data-dependent. At the end, we insert setup instructions to the program to embed the branch dependency information. Set branch ID instructions assigns an ID to the branch, and we use a set dependency instruction to set the branch dependency of the next instruction block. For example, we insert a set dependency instruction at the beginning of basic block 2, specifying that the next 8 instructions are dependent to branch 1. As you can notice in this example, the first 4 instructions in basic block 4 are independent from branch 1, but it's possible that they are dependent on an earlier branch, like branch 0. When we extract the branch dependency information by the compiler, we want to have an efficient design for the microarchitecture to exploit this information. In the front end of NOREBA, we gather the branch dependency of the instructions. When an instruction is decoded, we check if the instruction is a branch. Then we update a table called branch ID table to keep the IDs of the branches. And if the instruction is set dependency, then we set a counter called dependency counter table that sets the dependency of the upcoming instructions to the branch that is specified by this set dependency instruction. In the backend of NOREBA, we have a lightweight implementation for out-of-order commit. The instructions are inserted to the ROB, and when they reach the head, we insert these instructions to an appropriate commit queue based on the branch dependency of the instruction. We have a table called commit queue table that keeps track of how these branches are distributed to the commit queues. We send the instructions to the commit queue containing the branch that these instructions are dependent on. At the end, we commit the instruction from the head of these commit queues. Also, we keep a table of recently out-of-order committed instructions called committed instructions table. This table is necessary because in case of a branch misprediction, we don't want to re-execute the instructions that are already committed. We use this table to drop out-of-order committed instructions that are refetched in the front end. A challenge in out-of-order commit is the recovery from exceptions. We build NOREBA on top of RISC-V instruction set architecture, which limits the exceptions to floating point exceptions and memory-related events. Floating point exceptions can be accrued and reported at the end of the execution. But let's look at this example for memory-related exceptions. In this example, we have an if-then-else statement, and we predict a path after the branch and we commit some instructions out of order after the reconvergence point. However, the problem arises if a branch misprediction happens and we start executing from the correct path and we face an exception. We need to save and restore the out-of-order committed instructions when the control is given to the OS. We introduce two new instructions in order to communicate the out-of-order commit state of the processor with operating system. For the evaluation of NOREBA, we use Gen 5 for the simulation and LLVM version 10 to implement our compiler paths. We use SPEC CPU 2006 and MyBench as the benchmark suites. Also, you can see the configuration of the baseline core that we use. This is a processor like Intel Skylake, and the size of RB is 224. And for NOREBA, we use 3 commit queues with 8 entries, which 2 commit queues are for instructions that are dependent on unresolved branches, and 1 commit queue called primary commit queue for other instructions. For the performance evaluation, we look at different modes of instruction commit. In-order commit is the implementation in the current processors. Non-speculative out-of-order commit is a safe version of out-of-order commit that all instructions are committed as soon as all the commit conditions are satisfied, like no previous unresolved branches and no previous unresolved memory accesses. NOREBA is our work. An ideal reconvergence out-of-order commit is an ideal version of NOREBA that the number and size of commit queues are assumed to be infinite. Branch speculative out-of-order commit is an aggressive out-of-order commit mode that instructions are speculatively committed even if an earlier branch is unresolved. This is considered to be the upper bound of NOREBA's performance. As you can see, NOREBA shows 22% performance improvement on average and up to 230% improvement for MCF application. Also, NOREBA can reach 95% of the upper bound in branch speculative out-of-order commit. Now let's look at 2 applications closer to see why we are getting these performance improvements. According to our analysis, MCF has the highest potential to take advantage of out-of-order commit implementation, and BZIP2 shows the lowest potential. This figure shows the distribution of critical branches for these applications. The y-axis shows the criticality of the branches. In other words, the number of cycles that the RB is blocked because of these unresolved branches. The x-axis shows the number of instructions in the RB that are dependent on these branches. In other words, these are the instructions that have to wait for the branch to resolve before they can commit. As you can see, the branches in BZIP2 are less critical compared to MCF, and there are more dependent instructions, which means most of the instructions in the RB cannot commit non-speculatively until the branches are resolved. On the other hand, MCF has fewer dependent instructions, and this means there are more opportunity for NOREBA to commit independent instructions, even in the presence of unresolved branches. Here we look at the cores with different sizes. We look at 3 cores that have RB sizes equal to 128, 192, and 224, and also other structures change as well. The results shows that in all these cores, we get close to the branch speculative out-of-order commit upper bound. NOREBA continues to scale when the core gets bigger. And this means that more resources in the core, with the more resources in the core, NOREBA has more opportunity to improve the performance. And this figure compares NOREBA with Prefetchers, since both these techniques try to address the issue of long latency loads. The interesting point is that the effect of NOREBA and prefetching is additive. And when we combine these 2 techniques, we can see the improvements from both these techniques. One reason is that prefetching allows the processor to continue execution when we have long latency loads. And NOREBA, on the other hand, allows the processor to release resources earlier and making room for more instructions to execute. We also analyze the power consumption of NOREBA alongside with the area overheads. As this figure shows, we only get 4% energy increase over the in-order commit implementation. This 4% overhead comes from the selective ROB and the extra tables that we use. The queues in selective ROB are simple FIFO structures that do not contribute much in the power consumption. And the average area overhead of the new structures is about 8%. So NOREBA gets 22% performance improvement with low overheads in power and area. As we have seen in this presentation, NOREBA is able to address all the challenges for efficient implementation of non-speculative out-of-order commit. We detect branch dependencies non-speculatively through the compiler and pass this information to the processor. Extra structures in the hardware allows the processor to exploit the compiler information and to efficiently commit independent instructions through different commit queues. Also, we are able to communicate the out-order commit state of the processor with OS in order to recover from exceptions. To conclude this presentation, we could see that efficient interaction between different layers of the system enables the general purpose processors to unlock efficiency and performance. NOREBA proposes a hardware-software co-design that provides a better resource management and shows 22% performance improvement with low overheads in terms of power and area. I sincerely appreciate this opportunity to present our work, and thanks for watching this video. Bye.